We're looking at random variables, and a random variable is something that's represented by a single numerical value which is determined by chance for each outcome. This would be an example of a quantitative variable, and we learned that quantitative variables have two types. There's discrete, which means there's a finite or countable number, and continuous, which has an infinite number within a range, such as heights and weights. The kind of table we're going to organize our information in is called a probability distribution, and we're typically going to be using a table because it's easy to organize your equations that way. And it shows all the possibilities of values for the random variable. It's similar to a frequency distribution, except the frequency distribution showed how many were in each category, and this is the probability distribution is going to show the probability of each value, but they look very similar to each other. So we have some equations here. A quick note that we're going to be using the population symbols for the mean and standard deviation. So we have the symbol mu for the population mean and the symbol sigma for the population standard deviation. And then another quick reminder that the standard deviation is the square root of the variance, and in these equations we need to calculate variance first and then take the square root to find the standard deviation. So you can see those equations there. For the mean, we're going to take each value of x, or each possibility, multiply it by its probability, and then add those all together. There's two different ways to calculate the variance. The way that I'm going to show you in the example is the first one, where we take each value of x and subtract the mean, square it, and then multiply that by the probability of that value for x, and then add those all together. The other way, which might be a little bit simpler and a little quicker to do, but it doesn't really show the difference in the mean part, which is what variance is. So how the spread out the data are gives you the variance. The variance this way is x squared times the probability of x, add those all together, and then subtract the mean squared. And again, the standard deviation of a probability distribution is just the square root of the variance. In this example, we're going to calculate the mean and standard deviation from a probability distribution. And you'll see I have the probability distribution with x and the probability of x. So this part of the table is the probability distribution. And I've just expanded the table so that we can do our calculations right next to where the numbers are. And I suggest that you set up your problems this way as well. So the equation for the mean was the sum of each x times the probability of x. So I'm just going to take each x, so x in this column is 0, times the probability of x, which was 0.528. And if I multiply that out, you get 0. And the next x is 1. Its probability is 0.36. And we get 0.360. Next x is 2 times its probability. .196. And we just keep going. You'll notice the probability for the last row says less than 0.0001. I'm just going to use 0.0001 as the probability. So there's our values of x times their probabilities. I added a row to the bottom where we can put the sum So we would just add all of these numbers that we just calculated together. And we know that the mean is the sum of this column. And if we add those all together, we get 0.5995. So the mean of this probability distribution is 0.5995. Alright, next column over. We're going to do some calculations to find the standard deviation. So first we have to find the variance, and the variance is going to be the sum of this next column. So we have each x minus the mean squared times the probability of x. Okay, so our first x is 0. We just calculated the mean, 0.5995 squared times the probability of x, which is 0.528. And that would give us, if we calculate that out, should get 0.19. Next to x is 1. The mean is still 0.5995 squared times the probability of x, which is 0.360. And that comes out to 0.058. Now I'm not going to write out the work for the rest of them. You get the idea. You can fill that in yourself, and I'll just write the values for the calculations. And the sum of this column is going to be equal to the variance. And if we add this column together, 0.529. So now we know the variance for this probability distribution is 0.529. And the standard deviation is the square root of the variance. And we get 0.727. Alright, so the context of the problem is we have a group of 5 babies, and X is the number that have green eyes. So we would expect then, since the mean is 0.5995, we would expect anytime we have a set of 5 babies that either none or one of them might have green eyes, because 0.559 is between 0 and 1. Alright, under the table we have unusual results. We learned unusual results is anything past 2 standard deviations away from the mean, and now we're going to start assigning a probability value to that. So we can use a cutoff of 0.05 for a probability, or about 5%. And you'll see that in some problems. We might sometimes use 0.01 or 1%. Sometimes you might see 0.001 or 0.005 or 0.0001. So each different problem might have a different preset cutoff that has been chosen, and you just have to make sure that you're using whatever cutoff a problem provides for you to decide if something is unusual. The last equation we're going to learn is expected value. Expected value is the same as the mean for a probability distribution. So expected value E is the same as the mean, which we learned the equation before as x times the probability of x, all added together. So we'll do one more example to show that one. So we have a club that wants to invest $10,000 to host a baseball game. Their ticket total will be $1,500, and that would give them a profit of $5,000. And there's a 20% chance of rain the day of the game, which means that they would sell no tickets and they would lose $10,000. So there's two potential outcomes for their investment of $10,000. And those potential outcomes are going to be our values for x. So let's make a probability distribution. So the first possible outcome is that they'll make a profit of $5,000. The other potential outcome is that they will lose $10,000. We know that the probability of having a rainy day and losing $10,000 is 20%. I'm going to change that to decimal point 2. And since there are only two outcomes, those two outcomes need to add up to 1. So the probability of not raining, which means they would play the game and make $5,000, is going to be 0.8. So the expected value is going to be the sum of x times the probability of x. And in this case, we only have two things to calculate. So we can take x times the probability of x. We'll just make another column coming over. So 5,000 times 0.8 would give you 4,000. And negative 10,000 times 0.2, calculate that, we get negative 2,000. So the sum of that column is 2,000. So our expected value is $2,000. So is this a good investment? The expected value is a profit because it's a positive value. So technically it is a good investment. However, it's quite risky. There's a 20% chance of losing $10,000, which may be a higher probability than they would like. So we can expect to make a profit because the expected value is positive, but that 20% chance does seem awfully risky.